Alright, now that we've learned all of our rules, now we get down to the fun stuff. This is when it really gets good. This is one of my favorite applications of derivatives. I'm sure you can tell by the tone of my voice. Again, I'm incredibly giddy and excited. Related rates. What are related rates? Good question. Glad you asked. So that's the first part. We need to understand, what is that? Well, a related rate is the rate of change of two or more related variables that are changing with respect to time. So this is where it's important that we understand implicit differentiation, because now whenever we are doing a related rates problem, all of our derivatives are going to be with respect to time. So it's going to be something dt. So for example, maybe you're a cabbage farmer, and the rate of change of the volume of a cabbage over time is related to the rate of change of the length and the height of the cabbage over time. Why did I pick cabbage? Really good question. I don't really know. I feel that cabbage kind of gets a bad rep sometimes, but to be honest, I'm not a huge fan of it either, so I don't know, but that's still an example. Alright, let's do some other examples, but let's first understand how to do these. So here are the steps we want to follow. Identify all of the given quantities and quantities to be determined. Make a sketch and label the quantities. Okay, we've done that before. Make an equation involving the variables whose rates of change either are given or are to be determined. Okay, we can write an equation. Using the chain rule, implicitly differentiate both sides of the equation with respect to time, because every derivative is going to be with respect to time. After completing step 3, substitute in the resulting equation all known values for the variables and their rates of change. So it's very important that we do the substitution after we do the derivative. And then, of course, answer the question in the context of the problem, because we know that we're always supposed to do that with context problems. Alright, so first one. A pebble is dropped into a calm pond. That's lovely. Causing ripples in the form of concentric circles, of course. The radius of the outer ripple is increasing at a rate of 1 foot per second when the radius is 4 feet. At what rate is the total area of the disturbed water changing? Okay, so first let's identify our quantities. So the radius is 4. The radius is increasing. So I have, let's draw a picture. Circle with a radius, right? Circle is getting bigger. What do I know? I know that dr dt, which is the rate of change of the radius with respect to time, is 1 foot per second. I know that I want to find the rate of change of the area, so dA dt is what I want to find, and I want to find this when r equals 4 feet. So this is going to be one of the trickiest things, is we need to understand we are going to be using a number of r equals 4, but r is not a constant. It's very important to be able to identify constants versus variables in these problems. R is not a constant. So we are not going to plug this 4 in until the very end. Alright, so what's our equation? Well, we're relating area, so I care about the area. So area equals pi r squared, right? Okay, so now we're going to do the derivative, but when we're doing the derivative, we're doing it with respect to time. So the derivative of area with respect to time is dA dt. Pi is a constant, so this is just going to be 2 pi r dr dt. So now I can substitute in the values that I know. dA dt is 2 pi. Now I can plug this 4 in, times 4 times dr dt, which is 1. So again, what I want to emphasize is I can't plug the 4 in at the very beginning, because if I did, then area is just a constant, and that's not true. I want to find the rate of change of area when r is 4. So I have to plug that in later. So now we can simplify this, and we end up with dA dt equals 8 pi feet squared per second. So then we answer in the context of the problem. area is increasing at 8 pi feet squared per second when r equals 4. Alright, that one was pretty straightforward. Let's look at something more complicated. So here we have a 10-foot long ladder is leaning against a vertical wall. The foot of the ladder is being pulled away from the wall at a constant rate of 2 feet per second. When the ladder is exactly 8 feet from the wall, how fast is the top of the ladder sliding down the wall? Alright, I want you to try to set this one up on your own. If you can do the whole problem, go ahead and do it. But try to at least set it up. I'll give you a hint. You're going to use a right triangle here. Okay? But identify the variables, identify what you know, the givens, what you're trying to find. Try to set this up. Pause the video, unpause when you're ready to check your setup. Okay, so I drew a right triangle, and this is kind of what's happening. I know the ladder is the hypotenuse, and that's going to be 10. That's a constant. It's important to identify that, or it's helpful to identify that. And then I'm trying to find how fast is the top of the ladder sliding down the wall, so that's what I'm going to call dy dt. And I know how fast the bottom of the ladder is moving away from the wall, so I know dx dt. I know x and I know y because I'm trying to find this when x is exactly 8. Remember, this is not a constant though, so this is actually a 3, 4, 5 triangle, so that's how I get y is 6. If I didn't know that, I could use the Pythagorean Theorem to find this side. But I need to know that side before I do the problem also. Potentially, actually. In this case, I do. I also know, again, dz dt is 0 because this is a constant. So now I'm going to use Pythagorean Theorem. So I want you to pause the video and try to find dy dt. Unpause when you're ready to check. Alright, so hopefully you ended up with the ladder is sliding down the wall at 8/3 feet per second. Because you got a value of dy dt is negative 8/3 feet per second. And the negative is telling us that the ladder is going down the wall. So that's okay. But then when we answer in the context, we say just that is sliding down the wall at 8/3 feet per second because context is important and we understand that. Correct. Good. How do we come up with that? So we have our Pythagorean Theorem. So there's two ways we can do this. They're doing the same thing, but this is where understanding that something is a constant versus a variable is very important. So I can just take the Pythagorean Theorem as it is and do the derivative of the whole thing. So if I do that, I get 2x dx dt plus 2y dy dt equals 2z dz dt, and now I can plug in all of my knowns. So x is 8, dx dt is 2, y is 6, dy dt is unknown, z is 10, and dz dt is 0. So then I simplify, and then I solve for dy dt, and that's how I get my negative 8/3. The other way I can approach this is because I know z is a constant, this is the case where I can actually plug that in before I do the derivative. In this case, it really doesn't matter. And in general, it really won't matter if something's a constant, whether you do that, recognize that before or after you do the derivative. But if I plug it in before, then I just get, for the derivative, 2x dx dt plus 2y dy dt equals 0 right away. Again, it gives me the same answer, so then my next step, I would go right to what I have in the green and the blue and solve. But it's just something I want to point out, that recognizing something's a constant, that's when you can substitute the value in before the derivative. Alright, next one. Water is pumped from a cone-shaped reservoir. The vertex is pointed down, 10 feet in diameter and 10 feet deep at a constant rate of 3 feet cubed per minute. How fast is the water level falling when the depth of the water is 6 feet? Whew. Alright. So I want you to try to set this up. I will give you a hint if you don't remember, and you could look this up. It's actually in the front of your book, or just Google. It's always there. Volume is 1/3 pi r squared h. So that's the volume of a cone. So I want you to try to set this up. Go ahead and solve if you think you know how, but at least set it up. Identify the knowns, the unknowns, draw a picture, all that fun stuff. Pause the video, do that, unpause when you're ready to check. Alright, so we've got a cone. I told you the volume of a cone. So what do we know? We know the rate of change of the volume. dV dt is 3 feet cubed per minute. Now, if you're confused on how did I know that's rate of change of volume, look at the units, feet cubed per minute. So feet cubed is a volume. So that's the rate of change of the volume. how fast is the water level falling? That is dH dt. So I'm trying to find dH dt, and I'm trying to find it when h is 6. So again, h is not a constant here. H is a variable. This is just the instance when I'm trying to find dH dt. The problem with this is my volume equation has a variable r, a variable h, and a variable v. So I have 3 variables in this equation. And so that's a problem. All of them are changing. None of them are constants. So in order to do this problem, and since I'm trying to find dH dt, I want to get rid of r. So I need to find a relationship between r and h before I do anything else. So conveniently, if we have a cone, we have similar triangles. Because if I was to take the cross-section of a cone, it creates right triangles. And if I know that the diameter is 10, I actually know that the radius would be 5, and the height is 10. So I know that r equals 0.5h, or r is half of h. So I'm going to take that relationship and substitute it into my volume equation. So volume is 1/3 pi times 1/2 h squared times h, which conveniently simplifies to volume is pi 12ths h cubed. So now I want you to go ahead and find dH dt. Pause the video, unpause when you're ready to check. Alright, hopefully you got that the water level is falling at 1/3 pi feet per minute. How do we do that? Well, we just take our volume equation now and we do our power rule. So the derivative of v with respect to t is dv dt equals, bring down the 3, so that's pi force, h squared times dH dt. Plug in the h at this point, plug in the dv dt. Again, remember, we cannot plug in the h until after the derivative. Solve for dH dt, and I get 1/3 pi. Now, I will admit, 1/3 pi is not a great number for us to use as telling, I don't know what that is. It's not very practical, I should say, but for the sake of practice, we're going to keep things in exact values for right now. Yes, the decimal equivalent would be much more practical as far as understanding how much is 1/3 pi. And I also want to just again reiterate how important, so this is the first problem where we've seen where it was crucial that we were able to get the volume, the function that we're taking the derivative of, in terms of just one other variable before we do the derivative. If we didn't do that, keep in mind we would have had to do the product rule, and then we would have run into a dr dt as well, because r is changing. But we don't know the rate of change of r either, so that would be a problem. Next, a bolt is pulled into a dock via a rope with one end attached to the bow of the boat and the other end held by a man standing 6 feet above the bow of the boat. If the man pulls the rope at a constant rate of 2 feet per second, how fast is the boat moving toward the dock when 10 feet of rope is out? So I want you to try this one on your own. I'll give you a hint. It's another right triangle. Okay, if you're confused on this image, it's another right triangle. So try this one on your own. Pause the video, unpause when you're ready to check. Alright, so we should end up with the boat is moving towards the dock at 5/2 feet per second. How do we come up with that? Okay, so here's my picture. Check out that sweet, sweet boat. So I called this x, this y, this z. I know y is 6, and y is a constant. So dy dt is 0. The reason why y is a constant is y is the man. The man is not changing in height. At least not that we know of. Z and dz dt are what I know. X is 8 at the instance that we care about. We're trying to find dx dt. So again, it's important to identify what's a constant. What do we know? This was a 3, 4, 5 triangle. If it wasn't, we could use Pythagorean Theorem to find out the x, the y, and the z in relation to each other. But Pythagorean Theorem is what we're going to do the derivative of. So x squared plus y squared is z squared. Again, y is a constant, so I could have plugged that in before I do the derivative. It's up to you. The other two I cannot. So I do the derivative. Now I plug in x, I plug in z, I plug in dz dt, solve for dx dt, get my 5/2 feet per second, and I answer the problem in the context of the problem. Last one. We're going to do this on part 2. Go ahead and try it if you want, otherwise just pick up with part 2.